Most of the problems in section 2.2 are going to look and resemble a lot of the way that we work the problem out using the definition of derivative, exactly like what we were doing in 2.1. However, the very last example, I'm actually going to walk you guys through a different form of the definition of derivative just to show you. This was the one that has some crazy factoring, and you're going to see that, but I just wanted to show you an example like that. You don't have to use that way. You can always use the alternative methods, which I'm going to go back over in this section. What we're looking at here is a derivative as a function. So we're also going to look at graphs of functions and see what the graphs of derivatives look like. And remember, derivative is always just coming back to the slope of a tangent line. And then that's how we're going to build up. So we use this definition of a derivative, which you guys have seen the lengthy process that we've been going through with these. And then what we do is we look at graphs, and then eventually we'll be able to get to our shortcut formulas, which will make life so much easier as we go over this. All right, so let's recall what we've been looking at so far. So f prime at a is just a way to write the notation for derivative at a specific point where x equals a. And then this was the difference quotient we were using, but again, the limit as h approaches 0. Now we don't have to use a, that's just at a specific x value. These two really mean the same thing as far as the process. We just have x's instead of a's. So if we use f prime of x, that's really showing us it's the derivative of a function at any point. And here, again, I'm just using f of x plus h minus f of x instead of the a plus h minus f of a. But it's still conducted the same way that we try to calculate the limit. And as we've seen ever since chapter 1, the derivative is now the new word that we're using, is the same as the slope of a tangent line, which is the same as the instantaneous rate of change, which is also the same as the instantaneous velocity. All right, so we're going to first take a look at 3 graphs here where we try to graph the derivative of this. So the graph of a function f is given. We're going to sketch, or I'm going to draw one in, and then we're going to sketch the graph of its derivative, f prime of x. So pause the video, go ahead as best you can, just draw a copy of this. And what we're going to do is we're going to make a table of values. And hopefully if you can get some sort of straight edge or ruler to help you draw in tangent lines throughout. So what I want to do is find at different special x values or on an interval, I want to figure out what is f prime of x, or just identify what the slope of the tangent line is. And if we don't know it specifically, we could just describe it. All right, so one thing I'm going to try to do here is I'm going to draw in a series of lines. And let's see, let's make them blue. So the easiest type of line to kind of identify the slope here is if we have horizontal lines, because the slope of a horizontal line is what, guys? It's 0. So right up here at the top, I'm going to draw in a tangent line. And where else do you think we could fit a tangent line that's horizontal? And these are going to be key throughout this course. So notice we have it here at the highest point, and then also over here at the lowest point, what we call the maxes and mins, and we're going to eventually come back to those throughout this course. So what I'm going to do right now is just write in, this horizontal tangent line occurs at this point here when x is 0. So I'm going to leave a little bit of space. I'm going to put a 0. And then it happens again at 2. So down here, I'm going to put a 2. So the slope of the tangent line is 0 when x is 0, and it's 0 when x is 2. So now for these others, I just want to kind of write intervals. So I want to look from -1 to 0. Now -1 is an endpoint, so I'm going to show where x is greater than or equal to -1, but less than 0. I'm also going to show the interval between 0 and 1. And then I have another little interval where the slope changes a little bit from 1 to 2. And then my last part here is going to be the interval from 2 to 3. Now 3 is an endpoint, so I can include the 3 here, but everything else I just have the less than or greater than symbols drawn here. So the way I'm going to describe this, let's go between -1 and 0, those x values. I'm going to use a different color here. Let's use orange. So if I were to draw on a tangent line here, imagine that looks like maybe we're going maybe up 1 over 1, so we could say the slope is a 1. And then if you notice, if we draw another one in here, or a series of them, all these slopes are positive, but they're getting less steep. So they're positive and actually decreasing. So all of my slopes in between -1 and 0 are positive values. So I'm just going to describe them as positive and decreasing. Now let's take a look between 0 and 1. Let's use purple here. So if I were to draw a tangent line right here, notice it's negative. And then this is a steeper negative slope. So imagine like this first purple line I drew in, maybe a -1/2, and then maybe we're going to like a -1, and then over here we could be almost at a -4. So all of those slopes are negative, and then they're becoming larger negative numbers, which means they're decreasing. So all the slopes of the tangent lines between 0 and 1 are negative, and they're decreasing. Now let's take a look between 1 and 2. So I'm going to draw tangent lines over here. So that's also negative. And then let's see what's happening. This is a slightly less negative number, which means they should be increasing. So between 1 and 2, our slopes are negative, but they're increasing. And then let's take a look. What color do I want to use here? I'll just go back to red. Between 2 and 3, so if I were to draw on a series of tangent lines, definitely a positive slope. And then if you look, they're getting steeper, so they are increasing. So between 2 and 3, our slopes are positive and increasing. So now what we're going to do is make a new general coordinate plane here. So what I had above is the slope, or is the graph of our function. Now we're going to graph what I have in this table. So let's do -1, 0. We've got 1, 2, and 3. All right, so between -1 and 0, our points are positive. I don't know exactly how high up they're going, but let's say they start right here. And they're positive, and then they're decreasing. And I know it's going to be 0 right here at 0. And it's also going to be 0 at 2. So if I'm positive and decreasing, that means I'm coming down through this point right here. And then between 0 and 1, we're negative, and we're still decreasing. So we're still going like this till we get to 1. And then when we're between 1 and 2, we're still negative, but then we start to increase. So we're going to go back up until we hit this 0 value here when x is 2. And then between 2 and 3, we're positive and we're increasing. So it's a general shape right now, but it kind of looks like a parabola a little bit. So we kind of get an idea of what the graph should look like. Again, I don't know how high up or how much it's increasing or decreasing, but we have a general shape for the graph of our derivative. All right, for example B, let's go ahead and just graph f of x is equal to the square, or the absolute value of x. So we know that's a V shape, and it's going to look like this. Again, pause the video to draw this. And then just some key points here. We know if we go over 1, we're going up 1. If we go over 2, we're going up 2. Same thing over here, -1, up 1, -2, up 2. So we have some points here that we could find our slopes. So we only have 2 pieces here, so we only have 2 lines or line segments. So if I want to make a table of x and then our derivative, and again, we're just looking at the slopes of the tangent lines here. So I could kind of look at the slope over here, the slope of any tangent line I draw in here, because it's already a line. If I were to draw on a tangent line here, anything tangent to a line is going to be another line. So I could draw on a series of tangent lines. All of these slopes, based on this graph, is going to be -1. And that's everywhere that x is less than or equal to 0. Actually, no, we don't want to do an or equal to. We're just going to say less than. I'm going to talk about that. right when x is equal to 0, we'll discuss that. But then on the other side, if I were to look at tangent lines here, these would have slopes that are positive 1. So when x is greater than 0, my slope is going to be positive 1. However, there is actually some types of non-differentiability where a function is not differentiable. So if I were to draw in, let's do purple, right here at this corner, I really don't know that it's going to be a horizontal tangent line because they could still be tangent and then angled a little bit, or like this. So I really don't know at a corner. It's actually one of the types of non-differentiability. So I really say it's undefined at 0. So now what we're going to do, draw a new coordinate plane. I've got a positive 1, a negative 1, and then just some other values on the x-axis. All right, so when x is less than 0, all of my derivative values, all of my slopes of my tangent lines are negative 1. So I'm going to put an open endpoint and then just draw a horizontal line going out that way. And when x is greater than 0, all of my slopes of my tangent lines are equal to positive 1. But notice f prime of 0 is undefined, or it does not exist. And we're going to talk about that in a little bit. All right, let's try one more like this. Let's go ahead and graph f of x equals x squared. So take a moment, make another coordinate plane, or do this on graph paper. So again, this is just a parent graph. I have a parabola with a vertex at the origin. If I move over 1, up 1 on either side of the vertex, over 2, up 4 on either side as well. So I get a nice parabola that looks like this. All right, so again, we're going to make a table of values for x, and then my derivative, or slope of tangent lines. Now here, I'm actually just going to separate this. This is not a corner. This is a nice round part right here at the vertex. So I have that this is 0, so I could draw in a horizontal tangent line right here at 0. So my derivative, or my slope of my tangent line, will be 0. Now, if I were to draw in, let's go to the right, if I were to draw in a series of tangent lines, they are positive, and they're doing what? Are they increasing? Are they getting steeper? Are they decreasing? Or are they getting less steep? They are getting steeper. So for all these values, we'll just say x is greater than 0. Our slopes are positive and increasing. Now on the other side, we're starting with negative slopes, and they're getting less steep. So the negative numbers are kind of, we'll describe this as increasing. So think if we had like a -3 as a slope, and then maybe it's a -2 and a -1, or a -1/2. So when x is less than 0, our slopes are negative and also increasing. All right, so when we go to graph our derivative, I know right here at 0, 0, I have a point. Going to the right, so let's say this is 1, 2, 3, and so on. Let's number these. All right, so I know to the right I'm positive and I'm increasing, so I'm going like this. I don't know if it's curving yet, but we'll explore that a little bit later. And then as I decrease, or go to the left of 0, I am negative and increasing. So everything here is negative, but then they're also increasing. So what it looks like we actually have here kind of looks like a line if we were to kind of look at the points a little bit more specifically and try to guess them. But we have something that looks like this. So we're negative and increasing when x is less than 0, and positive and increasing. So we can match this to a line, and then this is the graph of our derivative. Even we wanted to go back here, this is the graph of our derivative. We want to label it as such. So there's going to be some examples on WebAssign that's going to have you match these graphs. So you could rule out ones that are so far from matching this. As long as you're close enough with some of the descriptions here, you're going to be able to match them in WebAssign. All right, so going back to the absolute value, we saw here at a corner, this was one of the types of non-differentiability. Actually, before that, let's talk about some notations for derivative. So we've already seen f prime of x. We could even see just y prime because f of x is the same as y. These are the three most common where we see dy over dx. That actually comes from delta y over delta x. This is the change in y's over the change in x, which is just the formula for slope. But dy over dx is another way to do that because this is the slope of the tangent line. So we're also going to see, I see this notation with like a d sub x and y. Some other ones that we really don't work too much with could be a d sub x of f of x, because f of x and y are the same thing. We could just see d of f of x, a derivative of our function. It might be, instead of dy over dx, it could be d over dx and then of f of x. So all of these really mean derivative, or we could just use, instead of dy over dx, df over dx. But these are the three most common ones that we're going to be looking at. And then it still stands to reason that the slope of the tangent line is just the limit as delta x approaches 0 of the change in y's over change in x's. But we really don't go back to this. This is just the difference quotient. Just instead of showing f of x minus f of a over x minus a, we just have change in y over change in x. But this is the definition of derivative that I had on the very first page of notes. All right, so a couple definitions, again, before we get into types of non-differentiability. This leads up to it. We say a function is differentiable at a point, at an x value a, rather, if f prime of a exists. So when we looked at the absolute value, I mentioned that f prime of 0 did not exist. So we can only say a function is differentiable if f prime at that x value we call a, if that exists. A function is also said to be differentiable on an open interval from a to b, that's using interval notation here, if it is differentiable at every number in the interval. And then not a definition, but a very important theorem that's going to link us to link differentiability to continuity, and then further theorems stem from this. If f is differentiable at a, then f is continuous at a. And it actually turns out that one of the types of non-differentiability happens at a discontinuity. So that's why we're saying if a function f is differentiable at a specific a value, then it's also continuous there. All right, so now for the, call it the four flavors or four types of non-differentiability. So we have corners. Go ahead and make a sketch of this. And again, this is just to show you that it's not necessarily enough of points here. It changes instantly, and we need a gradual change. So if I were to draw in a series of tangent lines here, that would be the same, and then all of a sudden, as I'm moving up this point, it changes instantly, and we need it to change gradually. So what's really happening here is I can't really say it's going to be horizontal because it could slightly almost teeter here. So at x equals a and x equals b, we say not differentiable at x equals a. Also, another example of a corner, not differentiable at x equals b. We need a gradual change in slope, not an instant where it just changes direction instantly here. So we need it to gradually change, and it does that with a nice curve, but not at a corner. Another type is considered to be a cusp. It acts kind of like a corner, so we might get something that looks like this. And then this, so right here is a cusp. And again, we would have a drastic change in the slopes of our tangent lines. So we could show tangent lines coming down like this, then all of a sudden they become positive. So we would say not differentiable at x equals a. Call that a cusp. And yes, there are some graphs that turn out to look like that. All right, a discontinuity. Let's say our graph is discontinuous at a, so maybe we have something that comes like this and then goes like this. So again, because we'd have to jump there to go from one part of the graph to the other, we would say not differentiable at x equals a, so for a discontinuity. And then a fourth type is what we call a vertical tangent. So this is what happens when we have something that looks like this, and then we almost have something too steep, and then it takes off this way. So right here in the middle, if we were to draw a tangent line, we would have a vertical tangent line. So again, we would say not differentiable at x equals a. All right, so as I mentioned before, we're going to relate calculus to a lot of physics-based problems. So here, if we ever try to map height and time, graph height as a function of time, um, we would get a parabola usually that opens down. And then height is always going to be in feet, time is seconds. So the derivative s prime of t is the instantaneous rate of change of height in feet with respect to time in seconds. So when we talk about the rate of change or velocity of an object, the unit of measure is always like miles per hour. Think of driving in a car. We have rate versus time. So we have miles per hour. We could have feet per second, meters per second. So those are the different rates that we could look at. So the unit of measure of this rate, s prime of t, is going to be feet per second. All right, so we have some velocity or physics related terms here. So position is usually going to be denoted with s of t or x of t. Velocity is the rate of change in position. So we use v of t, which is going to equal s prime of t, or v of t equals x prime of t. Just to save space for the rest, I'm just going to put this in terms of s of t. Now acceleration is the rate of change in velocity. So acceleration, which is a of t, is going to be the derivative of v of t, or a second derivative, s double prime of t. So a of t is equal to v prime of t, the derivative of velocity, or s double prime of t, the second derivative of position. And then this goes on for a little bit further, but imagine, and you've heard this word before, a rate of change of acceleration is actually called a jerk, and not a mean name, but you ever get like jerked around in a vehicle or on a roller coaster? So a rate of change of acceleration is called jerk. So this would be j of t, which is the derivative of acceleration, or the second derivative of velocity, or guess this last one, it would be the third derivative, so s triple prime of t. That's all the further we go with the primes. So we have a prime of t, v double prime of t, s triple prime of t. After that, it would look like the fourth derivative of position. We just start to see like little exponent notation, but that just means the fourth derivative of position. All right, so let's do a few more examples using the definition of derivative. So go ahead and copy this down. Let's use everything with x instead of a. So we want f prime of x, the definition of derivative, which means we start with the limit as h approaches 0. But rather than f of a plus h, let's just use f of x plus h minus f of x all over h. So there's no pretty way through this. This is going to take some time. This is where we really hone our algebra skills. So this is going to become 4 times x plus h cubed. It's our favorite thing to do, is cube that binomial, minus 3 times x plus h squared. So that's all f of x plus h minus f of x. So I have to keep it in brackets because I'm subtracting a binomial. And then this is all over h. Keep writing that limit notation. Notice it's after the equal sign. So we've done this a couple times. So here's a quick way to do this. If I cube the x, that's just going to be x cubed. And then the next two terms, there's going to be 4 terms altogether. The next 2 terms have a coefficient of 3. And then my x cubed goes down a degree, so x squared, and then my h shows up. Then I have another 3. My x squared just goes down to an x, but then my h degree starts to increase. So notice all of these add up to 3. I have a 3 here, I have a 2 and a 1, which is 3. I have a 1 and a 2 for the exponents, and then I have an h cubed. Next, I'm going to have minus 3 times, if I square x plus h, that's going to give me x squared plus 2xh plus h squared. And then I can subtract a 4x cubed and then subtract a negative 3x cubed, so plus 3x, or squared rather. And then this is all over h. Let's distribute. So we have the limit as h approaches 0. We'll have 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed minus 3x squared minus 6xh minus 3h squared, almost done, minus 4x cubed plus 3x squared, all of this over h. Some things should cancel. So let's see, we have a 4x cubed here, minus 4x cubed, so those are gone. I have a negative 3x squared, positive 3x squared, and those are gone. I think that's all I can combine. Now to save a little bit of writing time, notice how the remaining terms all have an h with them, and then I can divide all of those terms by this h down here. So I'll have the limit as h approaches 0. So I'm just going to take one h factor out of each one. So now this becomes 12x squared plus 12xh plus 4h squared minus 6x minus 3h. And I think I got all of them. So now we can actually do direct substitution. Wherever we see an h, that's actually going to turn into a 0. So right here, if h is 0, this whole term becomes a 0, because 0 times anything is 0. Same thing here, and same thing here. So we lose those terms. I no longer need the limit notation because I have what remains, 12x squared minus 6x. And that is f prime of x. Now you're going to see in a couple more sections, there's going to be a nice shortcut way to get to this, and we could check. So if some of you already know this, you can go back up and use that shortcut method right here with the power rule and see if that's what you get. A 12x squared minus 6x is what our derivative is at any x value that we're looking at. All right, now this next one, I'm going to show you guys a slightly different way to do this. Here, I still want to use a definition of a derivative, but I'm going to use f prime of x is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So there's going to be quite a few steps. We get into a lot of factoring. So if you're not a fan of factoring, I would maybe look at this problem once and then keep using the other method that we used here, the limit as h approaches 0 of this difference quotient. All right, so it's a little bit easier at the beginning. So f of x is just x squared. What's a little tricky about this problem too is that we just have a rational expression. So f of x is x squared plus 1 over x plus 4 minus f of a is a squared plus 1 over a plus 4. And then this is all over x minus a. So right away, that looks a little intimidating here. But what we want to do next is clean this fraction up, this complex fraction. So I want to multiply the top by the two denominators, x plus 4 and a plus 4, the clear denominators, and then I need to multiply this down here. So because that's a binomial, I want to put it in parentheses. We still have x plus 4, a plus 4. So we get limit as x approaches a. So when I multiply this LCD by the first fraction, the x plus 4s are going to divide out, and that leaves me with x squared plus 1 times this other part here, a plus 4, minus, and since I'm subtracting, I have to keep this in brackets. When I multiply this LCD by this fraction, the a plus 4s are gone, so I end up having a squared plus 1 times the x plus 4. And then now this is all over x minus a, x plus 4, a plus 4. Ultimately, if x is going to approach a, this x minus a factor down here can't be there. So there's got to be a way I need to get rid of it. And if I go to the top here, the numerator, if I expand it, rearrange the terms, and try to factor, that should happen. It's just a lengthy process. We have to be factoring masters at this point. So let's go ahead and just distribute here. So I'm going to get ax squared plus 4x squared. Inside, I'm going to get plus a and then plus 4. Over here, I'm going to get a squared x, a squared times 4, so plus 4a squared. Inside, I'll get a plus x, and then at the end, I'll get a plus 4. And this is all over x minus a, x plus 4, a plus 4. All right, Let's distribute the negative. Even if we try this one the other way, what we did on the last problem, it's still going to be a lengthy process. So we have ax squared plus 4x squared plus a plus 4 minus a squared x minus 4a squared minus x and then minus 4. And again, all over our denominator. All right, so we can go and cross out some terms. Let's see. I think it's just going to be the 4's. Plus 4 and minus 4 are gone. I don't see anything else. All right, so what I want to do, still keep the limit as x approaches a. I want to try to get all the terms that like have an x squared together, but I want the x term to go first. So let's start with like the 4x squared and a 4a minus 4a squared. So I'm going to put those together first because they have 4's in common. So 4x squared minus 4a squared. And I want whatever they have in common, the x's to go first. So notice next I have an ax squared and then minus an a squared x. Let's do those next. Plus ax squared, so the x squared part, I want that to go first, minus a squared x. And then I have last a plus a minus x. So let's put the x first. Minus x plus a. That looks good. Then we have x minus a all over this denominator, x plus 4, a plus 4. All right, so now what I'm going to do is factor out the common factors here. So the first two terms, this is called factored by grouping. I group the first two terms together, then I have the middle two terms, and then the last two. So I have a 4 in common. What's left is x squared minus a squared. Middle two terms, I can factor out an ax. What's left is x minus a, so that's a good sign. That matches the x minus a below. And of my last two terms, I could factor out a negative. What that leaves me with is x minus a. So I'm very close. All right, so let's continue this. I have one more factoring to do, and that's right here. So now this becomes 4 times difference of squares, x minus a, x plus a, and I just recopy everything else. So kind of like with the h's, now I can cross out the x minus a's from everything. So that means every term up here has an x minus a factor, and likewise down here. So this can all cross out with this down here. That means I'm taking each term and dividing it by the x minus a. So now this becomes, the limit as x approaches a, of 4 times x plus a plus ax. Now there's nothing left here, which is really just a 1, so minus 1. And then this is all over x plus 4, a plus 4. Like I said, the factoring is a little bit crazy here. Now all I have to do is replace all of my x's are approaching a, so it's getting closer and closer to a, so I could substitute a's in everywhere. So I no longer need the limit notation. This becomes 4 times a plus a times a. So all my x's are turning into a's, minus 1. And our denominator, x plus 4, becomes a plus 4. And then we have another a plus 4. So what we have here is 4, this is 2a, so we're going to get an 8a plus a squared minus 1 over the quantity a plus 4 squared. All right, so again, this was f prime of x, or really f prime of a, because x was approaching a. So that's what this just turns out to be. Like I said, I just wanted to take you guys through this process, no matter which way we determine this, other than the shortcut that we will see in the very near future. This was the process we had to go through. Let me know if you guys have any questions.